And good afternoon, everyone. On my behalf, also thank you for joining to this late session. Most probably, you must be really interested to this topic. My name is Vahid Javaheri from University of Oulu, Finland, Center of Advanced Steel Research, particularly from Microstructure and Mechanism Research Group, where our team actually is aimed for the fundamental research to develop and to understand the novel advanced high-strength steel using correlative multi-scale characterization and recently also multi-scale modeling. The title for my talk today is Dual Nature of Written Austenite on the Mechanical Property of Advanced High-Strength Steel with and without presence of hydrogen, which is based on a preliminary result of an ongoing research that we have just started. So we don't have all the result yet, but the current result that I'm sharing, it can be used as a foundation for the further discussion and feedback. I would like to mention also that all the material which I'm presenting here today has been developed and produced with our team with the contribution from this brilliant individual that you can see their name, and also we collaborated with Professor Ehsan from Jönköping University, Sweden. So let's move to the last thing first. So take away message. So after this, you are good to go. So you don't need to wait here. So the main message actually I want to deliver today is the fact that the complexity is the main characteristic of the modern and nowadays advanced high-strength steel, which offer an excellent mechanical property, but at the same time, it can increase their susceptibility to the embrittlement by hydrogen. So here you can see an example of the bright field TEM image covering an area of almost 1.5 micron by 1.5 micron and showing key and small macrostructural feature. We have equiax ferrite, different morphology of written austenite, very small cementite precipitation, fresh martensite, and also a strain-induced martensite only in this tiny area. And this interface between these features that I'm showing here can be meaningfully, the cohesion between this interface can be increased by the hydrogen and make it easier to cleave and also cause a sudden and unmature failure. For many technical, technological, and economic reasons, we cannot exclude the advanced high-strength steel from the future energy ecosystem. So as a materials engineer, actually, we should make significant effort to develop or to improve this advanced high-strength steel to be less susceptible to the hydrogen embrittlement. So as a very late introduction on the importance of advanced high-strength steel, I would like to share an impressive statistics. Actually, since 2022, when Volvo XC90 has been released in UK, there have been no fatal car crashes in UK and most probably in many different other countries. And this is largely attributed to the use of different advanced high-strength steel in this car body structure. So if we look at to the different generation of advanced high-strength steel, we can see that this third generation was developed to compromise or to address the drawback of those two previous one. I mean the lower ductility of first generation and higher cost of the second generation, and this is the area of our research. So on the right-hand side, you can see our current development. On one end of the spectrum, you can see we have a steel which exceeds 2.5 gigapascal in strength, and on the other, we have excellent combination of elongation and a strength level. So the product of elongation and strength level is about 60,000 megapascal percentage. Usually these third generation advanced high strength steel achieve their ductility, enhanced ductility through the stabilization of written austenite and the trip effect. We have heard enough about this trip effect during these conferences. So just as a summary, the trip is transformation of written austenite to the strain-induced martensite during deformation, which postpone or delay and sometimes also prevent the necking phenomena. Thereby, it increases the strength and ductility at the same time. So here is an excellent demonstration of the trip effect done by a friend of mine, Professor Bin Hanson, for the different strength level for the different austenite morphology. So you can see this transformation of austenite to the strain-induced martens. Usually we have two main approaches for the austenite stabilization: quenching partitioning and intercritical annealing treatment. So no time for a story. To keep it brief, usually we use quenching partitioning for our medium carbon steel, which resulted in very tiny film-like written austenite trapped between martensitic glass, and we rely on intercritical annealing for our medium manganese and lightweight steel. In this case, the written austenite morphology and fraction is depend on the initial macrostructure and processing route. As you can see here, if we do the intercritical annealing after hot rolling, we get the lamellar type of written austenite, which follows the orientation relation between martensite and austenite. So austenite grow along the martensitic block boundary and last boundary, and ended up with this up to 40–45% lamellar type of written austenite. After cold rolling, we introduce a lot of dislocation and sub-boundary. And if we do the intercritical annealing after cold rolling, what we get is the crystallized ferrite. And for the austenite, it's not necessary actually to grow with the orientation relation with the parent martensite. So there is an energy for austenite to grow and make this equiax type of very tiny equiax of the written austenite. And then we can get up to 50% depending on the time and temperature of intercritical annealing. And if we do intercritical annealing after warm rolling, we can get advantage of both macrostructures. So we can produce both equiax and laminar written austenite. So if I translate this macrostructure to the actual mechanical property, you can see the result can vary a lot among them different macrostructure. For example, the trip effect and work hardening is very prominent here with the sample that has been intercritically treated after hot rolling. And with this condition, we get excellent uniform elongation and almost a fully stable written austenite. As I mentioned at the beginning, our main goal is to study the effect of different morphology and fraction of austenites with and without presence of the hydrogen to check the response of this macrostructure. But unfortunately, we have received the result only for this macrostructure. Let's say 40% written austenite for our medium manganese steel. And for comparison, we selected also two quantum partition steel, the carbon steel with almost the same morphology, but different fraction of written austenite. Usually what we observe is there is a difference between the measured fraction of written austenite with XRD and EBSD. And you can see here the reason why. So the thickness of this austenite film sometimes exceed the EBSD resolution limit. So usually we rely on lab XRD and sometimes also on high energy XRD to measure the actual fraction of written austenite. So we did the ex-situ electrochemical or liquid charging. You can see the condition here. So we use sulfuric acid and we apply current density of 3 milliampere per square centimeter. And for 24 hours, immediately after charging, we did the slow strain rate tensor test and with the strain rate of 10 to minus 6. And believe me, as an engineer, this is the rate that you should do the test to see the effect of hydrogen in this kind of a state. So this is the result that we get from the SSRT test. And depending on how you choose to interpret these results, one can argue considering the amount of total hydrogen and also the rate of strain that we apply, that there is an improvement. But I would conclude that at the end of the day, if we have a continuous exposure to the hydrogen, we lose whole plasticity in all the samples, which is not actually the topic of my today's talk. So let's move to examine the fracture surface. So for our medium manganese steel, if you remember that 40% written austenite, we have fully ductile behavior for the uncharged sample. When we charge it with hydrogen, we have fully brittle fracture. And for this quench partitioning steel, we have a mixture of brittle and ductile behavior with the uncharged sample, and again, fully brittle fracture with a lot of secondary and deep secondary cracking, and almost the same behavior for the other quench partition. So here you can see this secondary crack, and if we zoom in this area, there are a lot of intergranular cracking that's, yeah, they are distributed everywhere. So if we do the cross-section examination, you can see very sharp crack along the prior austenite grain size. So these are the area that we did the examination near the fracture surface. So if we go a little bit far from the fracture surface, we can see this kind of zigzag fracture, which is actually the transgranular to the prior austenite grain size. But in this phase map, we can see the indication of the strip effect. Because of the morphology of written austenite, these images are not a good example for this strip effect, but for the medium manganese steel, actually what we did, you can see here in this area, very far from this gauge area, very far from the fracture surface, we have, in this measurement, we have 30% written austenite. As I mentioned, it follows the orientation relation between martensite and austenite. So you can see that they have orientation of this deformation. And when we do the EBSD very near to the fracture surface, in many areas, we have only 10% written austenite. In many areas, this austenite is transformed to the martensite. And they are actually with a different orientation. So to summarize my talk, this complex system, complex macrostructure of advanced high-strength steel, there are a lot of interface. It doesn't matter how much hydrogen we are going to trap. In some extent, we have a mobile hydrogen, so the crack initiation is unavoidable. What we can do as an engineer, maybe we should work to arrest those cracks. And if we have a stable austenite, because the solubility of the hydrogen is much greater in the FCC structure, we have enough source of hydrogen near to the interface. But if we have a trip, if these FCC transform to the other structure, so hydrogen have to escape from FCC structure and actually release a lot of hydrogen on the surface and cause another actually site for the crack initiation and crack propagation. So the next step for this research is working on the making the crack actually arresting feature in the macrostructure, and do also the same thing for the other macrostructure. So by thanking the financial support that we have received, I will close this talk. Thank you. If you have any question, you are more than welcome.